Now we're recording. So welcome to Advanced Modeling Methods again. This is lecture 11, right?
Yes.
Lecture 11. So Advanced Modeling Methods. Lecture number 11. All right. So we've been talking about the boundary element method, and we got to a point where we can actually framework the boundary element method, how it works. Take a problem, as long as the problem is well posed. Make sure. Let me see if I'm recording. Now I'm paranoid with these. Yes. So make sure the problem is well posed, it's solvable. And after you determine that, you take the boundary of the problem, discretize it into elements, and then decide what type of elements you use. So far, we've only been talking about the constant superparametric elements, basically linear geometry and a constant node right in the middle to denote the field variable. And then we ended up with the so-called discretized BIE, boundary integral equation, co-located at I equal 1 through n boundary nodes. So we collocate the BIE at the n boundary nodes, which are the center of each of the n boundary elements. And the result of that was Ci Ti plus the summation from j equal 1 to n of Hij Tj is equal to the summation from j equal 1 to n of Gij Qj. Okay? Such that these kernels, Gij, is basically the integral over element j, over boundary element j, of g, and I'm going to now write the entire dependency for a particular reason. Before we were just writing x and psi, but now denoting that this is specific to 2D, because we've been developing the method for 2D, I'm writing the full dependency, x, y, xi, and yi. This is a field point, and this is a source point of the Dirac delta function. And Hij j hat is equal to the integral from delta over element j, h, x, y, xi, yi, theta. All right? So, who is element j? Let's say that this is element j. And element j has a node in the middle, which we call, well, that's the field node, and these two nodes, x2, y2, j, which are the ones that define the geometry of the element. x1, y1, and x2, y2 define the geometry of the element because we said that the element was linear. And the normal vector in the outward direction, assuming that that's the inside of the domain is here and the outside of the domain is there, the normal vector points in that direction. And remember that the boundary omega is a summation of these. The whole boundary of the domain, however many boundaries the domain has, because it can have internal boundaries as well, like poles, for example, are defined by these collection of segments or boundary elements. All right. So how do we conduct these integrals? Okay, we're integrating over a linear segment from a point x1, y1 to a point x2, y2 of a function g or a function h, whatever that function is. We know that g looks like a log, and h looks like 1 over r, or 1 over x, or square root of x minus xi squared, y minus yi squared, and so on and so forth. How do we conduct, in general, an integral that is over a segment? We need to do a line integration, right? So we need to parameterize x and y. These are the field variables of integration. We need to parameterize x and y in terms of a parameter that is valid from this point to this point, and we need to parameterize the boundary, or the segment, or the line, with respect to that parameter. There are many ways of doing this. But in this case, it's very simple because the line of integration is always a straight line. Okay? So the parameterization will always be very simple. So, in general, let's formulate the solution of an integral of the form. Let's say that I is equal to the integral over the segment of some function f of x and y d gamma. Don't worry about xi, yi, because that's another dependency. Okay, that's what defines the function. But just basically integrating with respect to x and y. All right. So what do we do? We have to parameterize x and y in terms of a single parameter eta, such that this segment somewhere in space from x1, y1, j to x2, y2, j, we turn into a segment in the eta direction that goes from eta equals -1 to eta equals +1. So this is node 1, this is node 2, this is node 1, this is node 2. Right? So we're basically going to map, linearly map, and linearly because this is a line, we're going to map this point to this location and this point to this location in terms of a parameter eta. I'm going to write what it's going to look like, but by inspection you can actually determine this. I'm going to write it in the form of basis functions. All right. So can you see why this will interpolate linearly to this? When eta is equal to -1, notice this goes to 0, right? When eta is equal to -1, and this one goes to 1, right? It's -1 minus -1 over 2 is 1. So x is equal to x1. When eta is equal to 1, what happens? Well, this one goes to 0 and this one goes to 1, so x is equal to x2. So this point maps to this point, and this point maps to this point. Same thing for y. Same thing. We're using the same shape functions. And the shape functions are basis functions. We satisfy the conditions and requirements of a basis function, right? They are 1 in its corresponding node and 0 everywhere else. Okay? There's only 2 nodes in this case. And if we evaluate this function at eta equals 0, what do we get? At eta equals 0, this is 1/2 and this is 1/2, right? So we get the average between x1 and x2. So the midpoint of this segment maps to 0.0 here in this line. Same thing for y. All right, notice n1 of eta being equal to 1 minus eta over 2, and n2 of eta being equal to 1 plus eta over 2, or linear basis functions. So essentially, we have eta 1 minus 1 and let's make this 1. So this is n1 of eta, and this is n2 of eta. So at eta equals minus 1, x of eta is equal to x1, and y of eta is equal to y1, and at eta equals to 1, x is equal to x2, and y of eta is equal to y2. So this is just linear mapping, or parameterization, something that we've done when doing line integration. All right. So basically, I, which is the integral, remember we're trying to formulate or solve this integral. Will turn out to be the integral from minus 1 to 1 of f of x of eta, comma y of eta, d of gamma of eta. All right, so whatever that function is in terms of x, we replace x by that x of eta. We replace y by that y of eta over that segment. We integrate between minus 1 and 1. And the only thing left to do is to formulate the differential of gamma in terms of eta. That one's pretty easy too. If you look at the element again, this is the element, delta gamma j. Again, this is x1, y1. This is x2, y2. And let's look at a piece of these. This will be d gamma, or a piece of the element. Right? And d gamma is basically the hypotenuse of a triangle that has a piece of y and a piece of x. So d gamma is nothing but the square root of dx squared plus dy squared. Therefore, d gamma is equal to the square root of dx, I can replace by dx d eta times d eta, and all of these is squared, and dy I can replace by dy, d eta square. I just chain rule both of them. And therefore, d gamma, instead, in terms of eta, is equal to square root of dx, d eta squared plus dy, d eta squared times d eta. And remember, these right here is called the Jacobian of the mapping or transformation. So we're performing a transformation of coordinates between x and y to a coordinate eta, and this is a Jacobian of the transformation of the arc length into the eta. All right? So who's dx d eta and dy d eta? Well, for this particular case of constant elements, but all of these is formulated in terms of linear elements. We didn't write it anywhere, but those are the elements that we're working with. The x d eta is equal to x1 of j times dn1 of eta d eta plus x2 of j dn2 d eta of eta, and dy d eta is equal to y1 dn1 d eta of eta plus y2 dn2 d eta of eta. If we look back at what the etas are, or the n's, we have them here. N1 is equal to 1 minus eta over 2, and N2 is 1 plus eta over 2. So the derivative of N1 with respect to eta is minus 1/2, and the derivative of this one with respect to eta is plus 1/2. They are constant because the mapping is linear. If the mapping was quadratic, we don't have constant, we have actual functions of eta. Such that the eta1 or the n1, the eta, is equal to minus 1/2, and the n2, the eta, is equal to plus 1/2. And therefore, the x d psi is equal to x2 minus x1 divided by 2, and dy d eta is y2 minus y1 divided by 2. All right? Again, that's because we're using linear shape functions for the elements. And this is okay, note, only for linear shape boundary elements. If we decide to use quadratic shape functions for the elements, so use 3 nodes to define an element, then the story is different. These functions are quadratic basis functions, and these derivatives will turn out to be slightly different. And the Jacobian is going to be a function of eta. In this case, it's just a constant. All right. So basically, we go back to that Jacobian. So the differential of boundary is equal to the square root of dx d psi, which is x2j minus x1j divided by 2 squared plus y2j minus y1j divided Now I can take these two outside, right? This 2 I can take as a common factor, the 2 square as a common factor, and then the square root of that is a 1/2 outside. So I end up with 1/2. Let's do it. 1/2 of the square root of x2 minus x1 squared plus y2 minus y1 squared. And who's that in the square root? Remember, x1, y1 is 1 point here, x2, y2 is a point here.
That's just
It's the length, right? That's the length of the element. So this, let's just call it LJ, length of element J. So is the length of element J divided by 2, dA. All right. So in general, the integral we're trying to solve, which is the integral over delta gamma j of any function, the gamma translates into the integral from -1 to 1 of f of x of eta, y of eta, length over 2, the eta, and therefore the integral is just simply the length of the element divided by 2 times the integral from -1 to 1 of f parameterized over eta d eta. So what was originally a line integral is now an integral over a single variable eta from -1 to 1. Now, this is not the only way you can parameterize segment and space, okay? You can decide to parameterize with other limits, not necessarily from -1 to 1. You can parameterize from 0 to 1, from 0 to L, whatever you want. And the metric or the Jacobian will be different, the shape functions will be different, but there's a reason why I decided to map the nodes 1 and 2 points eta, -1 and 1. There's a reason why I want this integral to go from -1 to 1. Because the numerical integration routines that we will use to solve these integrals operate on the range from -1 to 1. Okay? You can take any integral you want from a to b and map it to an integral from -1 to 1. You just got to do a variable transformation, right? And this is what we've done. We just taken an integral that is an integral, a line integral in the 2D plane, turn it into a 1D integral, and the limits of integration turn it into -1 to 1. And again, the reason is because the numerical integration routines operate between -1 and 1. All right. So, what else do we do? Well, the function f, in our case, are, well, this one, which is -1 over 2 pi log of the square root of x minus xi squared plus y minus yi squared. That's the function g, right? And the other one is a function h. function h requires the normal vectors of the specific element in which they're operating, because it's basically the normal derivative of g is grad g dot n, such that is equal to grad g dotted into the normal vector. And that's how we end up with that. Is dg dx times nx, dg dy times ny. All right. So we also need those normal vectors. We know how to integrate a function now. Any function of x and y we can integrate between -1 and 1, as long as we have the length of the element, and that's easy to find. That's x2 minus x1 squared plus y2 minus y1 squared, square root of that. But we also need to find those normal vectors. If I give you an element that has a starting point at x1, y1, and an ending point at y2, y2, can you find the coordinates of the unit normal vector that points out of the domain? Well, in 2D and linear elements, very simple. The normal vector. So again, if we have this is delta gamma j, and that's assuming that the domain is here. If the domain is here, the normal vector is here. The normal vector, remember, has a coordinate x in the x direction plus a coordinate y in the y direction. And it's unit in length. Essentially, the sum of its components, the square of the sum of these components, or the sum of the squares of its components is 1. This goes from x1, y1 to x2, y2. In general, nx, see, assuming that this element right here could actually be curved, not necessarily a straight line, we could calculate the coordinates of that, or the components of that normal vector at any point along this line from eta equal -1 to eta equal 1. Remember, the spin parameterized from eta equal -1 to eta equal 1. And x is equal to the derivative of y with respect to eta divided by the square root of the x, the eta squared, plus dy, the eta squared. And ny is equal to minus the x, the eta, the x, the eta squared plus dy, the eta squared. Now I can put in the numbers there. For the case of linear or linearly shaped elements, nx is equal to, nx of element j is y2 minus y1 divided by the length of that element, and y j is equal to minus x2 j minus x1 j divided by the length of the element. All right. This is for the case of linearly shaped elements. In general, you'll have to do it like this because if you have an element that's curved, the normal vector is a function of the position eta. It changes the coordinates of the normal vector. But it's guaranteed that the sum of these components will be 1. Okay. Note nxj squared plus nyj squared is equal to 1. It's guaranteed that that's equal to 1. This one squared plus that one squared will give you 1, because this one squared plus this one squared is equal to the length. The numerator is equal to the length squared, and the denominator is the length squared. So this is how you calculate the normal vector of every element. The field point, or the field value node. Remember, we're talking about subparametric elements. And subparametric elements have a node in the middle. So this is x1, y1, j. This is x2, y2, j. And this is xm of j, ym of j. We can call it the midpoint, or we can call it the field value point. Xm of j is equal to x1 plus x2 divided by 2. Well, ym of j is equal to y1, y2 divided by 2. Right? This is basically where we place the Dirac delta function, and we do it at every element during the collocation process. The source point of the Dirac delta function we locate at the center of each element so that we can generate a matrix system like we did last time. All right. So after collocation of the Dirac delta function source point psi at the field value node of each element xm ym we end up with the summation from j equal 1 to n of hij tj is equal to the summation from j equal 1 to n of gij qj, such that I goes from 1 to n. So we have this algebraic system that connects all the temperatures of all the boundaries to all the fluxes on all the boundaries. Okay, through these kernels H and G. Remember, hij is equal to the hij components that we've been calculating on that integral plus Ci delta ij. We already defined this. Because remember the BIE, the discretized BIE had Ci plus Di here. Okay? And this was Hij hat. So we combine the Hij hat with the Ci by adding only to the diagonals. Remember that Dij is the Kronecker delta. So it's that D delta Ij is equal to 1 if I is equal to J, and 0 if I is different than J. It's just an identity matrix. So we basically added Ci to the diagonals of the matrix Hij. We went through a hand exercise last time to look at the matrix. Recall, and Ci is equal to 1/2. In our case, because we never place a node at any corner, all Ci's are equal to 1/2. By placing the source point of the derivative of the function anywhere on the boundary, the integral only sees half of that derivative of the function. That's why that Ci is equal to 1/2. Remember, that came from the sifting property. It's the integral of the derivative of the function times the temperature. So you only see 1/2. If you were to place a derivative of the function at a corner, at a 90-degree corner, if you would have a source point, a field value node, right at a 90-degree corner, Ci will be 1/4. You will only be able to see 1/4 of the effect of the derivative of the function. But we'll never do that because there'll never be a node at a corner, a field value node. Because the field value node is at the center of each boundary element. And the center of each boundary element will never be at a corner because our boundary elements are linear. Okay, so remember that. Now, all right, so we have this. In order to find these elements, or these elements, we integrate. In order to find these elements, we integrate, we connect, and we have a system. All right? So there's something else that we need to be aware of. Let me show you again. That's my computer. Maybe somebody's texting me and it's connected to. Let me check. No, it's not my computer. All right. Sure, I'm not.
Your battery?
No, battery's fine. All right. That's fine. All right. So let's look at the functions we're integrating, and you're going to tell me something that could potentially happen. We know now how to integrate a function of any kind over a boundary element, just a line in space. We parameterize it between -1 and 1, and we conduct the integral by whatever means of integrations we know. All right? We can potentially integrate it analytically, or we can do maybe a numerical integration like trapezoidal or quadratures, which we're going to learn in a very effective way in class. But tell me something about this integral. The function we're integrating is this. Let's concentrate on the g. We're integrating that function. So, all right, so we have a source point here. Somewhere here, we have a source point. And then we're integrating over a boundary element that's here. Remember, we put the source points over all the boundary elements. So let's say we put the source point here, and we're integrating. We have to integrate over all the elements, right? We're integrating over an element here. It's fine, right? The source point is here. The boundary element is here, between -1 and 1. The log will never be weird, right? Because xi, yi is somewhere here. And we're integrating between here and here, right? But what happens when we're going around and integrating over the entire boundary? What happens when we have to integrate exactly on the element that contains the source point? Look at the integral, it's singular, right? We have, at some point during that integration between -1 and 1, exactly at 0, what's going to happen is that you're going to integrate over a log of 0, and the log of 0 is -infinity. So you have a singular integral. And you cannot handle singular integrals with numerical integration. right? Numerical in the trapezoidal will not be able to handle singular integral. So we need to come up with a rule to be able to do that. Or try to find out whether that singularity we can avoid. Because one thing is that the integrand is singular. But however, that singularity might be avoidable. It might be a weak singularity. And that singularity might disappear when we integrate, because remember, we're multiplying times an area. In this case, times length. All right? So those elements where we're integrating over the element that contains the source point are singular value integrals. Those are singular value integrals. And those are exactly the diagonal components of the matrix H and the matrix G. The diagonal components of the matrix H and the matrix G correspond to the locations of integration that contain the source point. So notice that the diagonal components or elements, let's call it elements. No, let's not call it elements. Let's call it components of the matrices G and H, i.e. GII and HII for I equals 1 through n, or you can call it GJJ or HJJ, same thing, contain singular integrals. Because the integration is carried out over the same element, delta gamma j, that contains the source point psi I. All right? So again, let's look at this. We're integrating between x1, y1 of j to x2, y2 of j, which we know now is eta minus 1 to eta 1. This is element delta gamma j, and somewhere in that element there is I, such that I is equal to j. That would only occur when psi is equal to j. That singularity will be exactly in the middle of the integration limits. So what do we do? We're going to take GII, let's start with GII, which is the integral from x1, y1, and let's call this I now, x2, y2, I, minus 1 over 2 pi log of the square root of x minus xi squared plus y minus yi squared d gamma. We're going to break the integral in half, recognizing that the singularity occurs exactly halfway through the integration path. So we're going to say GII is equal to the integral from x1, y1 of I to xi yi, that's location of the source point, of minus 1 over 2 pi log of x minus xi squared plus y minus yi squared d gamma plus the integral between xi yi to x2 y2 I of minus 1 over 2 pi log of x minus xi squared plus y minus yi squared d gamma. All right. Now this function, this integrand, is even. See? Because it has a square root and the square terms, this integral is equal to this integral. Because these points are equidistant from each other. So this one is equal to that one. Note that. The first integral is identical to the second one because the points are equidistant and the integrand is even. So GII is just simply minus 1 over pi, so it's twice either of the two, and I'm going to pick the second one, log of this much. All right? So I'm going to conduct a different parameterization. I'm going to parameterize so I can integrate from 0 to 1. Okay? Parameterize gamma to eta such that eta goes from 0 to 1. And that will be x of eta is equal to x2 minus xi of eta plus xi. So when eta is equal to 0, we get xi, and when eta is equal to 1, we get x2. And y of eta is equal to y2 minus yi, eta plus yi. Recall, the gamma is equal to the square root of the eta squared plus dy the eta squared times the eta and therefore the eta is going to be equal to the square root of x2 minus xi squared plus y2 minus yi squared the eta. And what is this? That's half the length of the element. That's the length between the end node and the mid node. And therefore, d gamma is equal to length over 2, the eta. All right. So we're getting somewhere. So GII is equal to minus 1 over pi, the integral from 0 to 1, and the log of the square root of x minus xi square plus y minus yi square times the length over 2 d eta. Alright, so I can replace x by its parameterization and y by its parameterization, right? It's minus 1 over pi log of x minus xi is equal to x2 minus xi times eta plus y2 minus yi times eta squared of j over 2 d eta. Alright, so I have GII is equal to minus L, I don't know why I call this LJ, this is actually Li. You see, length of element I. Yeah. It's Li divided by 2 pi, and this would be the integral from 0 to 1 of the log of, I can call this L, half L square, I can take n as a common factor, and this will be Li times eta over 2 d eta. Alright, and integrating by parts, results in GII is equal to minus Li over 2 pi times eta times the log of Li eta over 2. This is how you integrate a log, you have to integrate by parts, plus minus eta between 0 and 1. Okay, this is a minus, but now I have to evaluate the log of 0 still, right? But what is 0 times the log of 0? So it's 0 times minus infinity, so it's undetermined. So you have to look at the limit, you apply L'Hopital's rule, and you'll find that the limit is actually equal to 0 because the log is a weak singularity and grows bigger than the log, right? So, recognizing that the log, the limit when x equals 0 of x log of x is equal to 0, then we can find that GII is equal to Li divided by 2 pi over 1 or times 1 minus the log of Li over 2. So that is the diagonal element of the G matrix. Again, only for constant elements. Again, this is only for linearly shaped elements with constant field value nodes. Those are called the linear supersymmetric elements, or constant elements in general. So, no need to evaluate the GII term numerically. You don't need to evaluate that integral numerically. It will be complicated. You can still do it by adapted integration, adapted numerical integration. But why go through the hassle of having to integrate when you can just use that for the diagonal element? All right. Now, what do we do about the other one, HII? HII is a little bit more complicated. How about HII, which is equal to HII hat plus 1/2. Right? Such that HII hat is equal to the integral between x1, y1, I to y2, x2, y2, I of h, which looks like minus 1 over 2 pi times x minus xi times nx plus y minus yi times ny x minus xi squared plus y minus yi squared. Began. Now we're looking at a strong singularity because we're dividing by r squared. And r goes to 0 at the center of the element. This one is strongly singular because the integrand goes to infinity as 1 over r squared, such that r goes to 0. See that denominator? Well, it is really 1 over r because on the numerator we also have x minus xi, y minus yi. So this is r divided by r squared. So I will say it like this. It goes like r over r squared. All right? Now, it turns out that because, again, the element is linear, we have a linear element. Because the shape of the element is linear and the coordinates or components of the normal vector n are always perpendicular to the components of r, which is equal to x minus xi, y minus yi, ey. So that's the numerator. So we have another 0 in the numerator. So the denominator has 0 squared, right in the middle of the integration path. The denominator goes to 0 squared, and the numerator goes to 0 here, and it goes to 0 because of the multiplication to the normal vector. So we have 0 squared in the numerator, 0 squared in the denominator, and then that singularity also becomes avoidable. A strong singularity becomes a weak singularity that actually goes to 0. In this case, we can demonstrate that HII hat is equal to 0. Therefore, HII, which is equal to HII hat plus 1/2, is just simply equal to 1/2. All right. Now, what if the elements weren't linearly shaped? Then HII hat is different than 0. The integral is strongly singular. And special numerical integration, adaptive integration techniques are necessary. Okay. But locally, we'll always be working with linearly shaped elements. I'm not going to ask you to implement a quadratic element because that will be too much to ask. I'm still thinking what to assign for the project. I thought about, okay, we're going to develop a code here in class that is based on linear elements, and I would ask you to, okay, make the element shapes quadratic and come up with your own shape functions and so on. But that's kind of probably too much to ask. I don't know yet. But in any case, or looking at the discretized BIE. All right, so we have these. Summation from j equal 1 to n of hij tj is equal to the summation from j equal 1 to n of gij qj. All right, so that discretized boundary integral equation after collocation should work for that geometry. Remember that h and g are only functions of geometry, right? H and g are the integration of the boundary elements of the log and the 1 over r and so on. This one contains the log, this one contains the 1 over r, and the 2 pi's and so on, right? So if I give you that same problem on that same geometry, you should be able to use the same h and g's, right? For any problem I give you on the same geometry. If I tell you now the temperatures are these different ones, you should be able to use the same geometry, the same g's and h. Okay? This is valid for any combination of boundary conditions. Any combination of boundary conditions, T and Q. So let's say that I give you a problem in a square, right? So you calculate all the elements. I tell you break up the boundary into 40 elements, okay? 10, 10, 10, and 10. And then you calculate all the G's, all the 40 by 40 G's, and all the 40 by 40 H's, right? You have these two matrices that are 40 by 40. And then I tell you, well, the temperature here is 0, the temperature here is 10, the temperature here is 20, the temperature here is 30. Okay? So you fill this out and solve for all the Q's. Right? AX equal B type of system. You can do it. Then I tell you, okay, I decided now that the boundary conditions are going to be 20, 60, 100, and 0. You can use the same H's and the same G's, right? And come up with a new set of Q's. It's going to be a completely different solution. The map, the heat map is going to look completely different. All right? Now, what if I tell you that the temperature here is 10, 10, 10, and 10? I give you all the temperatures on the boundary are the same, 10. What is the solution to that problem? 10. Well, the temperature, yes, is 10, right? But the solution in this case, if I give you all the temperatures equal to 10, what is it you should get for Q's? If I give you a problem where there's no temperature gradient, you just said it, the temperature is 10 anywhere, what is Q? 0. You should get 0 for Q if I give you all T's the same. Okay? So let's assume that. Now assuming that all Tj's are equal to a constant, C, I'm just going to call it C, for J, 1 through N, this is called the equipotential. Then, the solution is Qj equals 0 for j equal 1 through n. Remember that we're working with the Laplace equation. There's nothing else generating energy here. It's just plain old heat conduction. If we had energy generation or the problem was transient, that's a different story. Okay? But because it's a steady heat conduction, it's just a Laplace equation. If all the temperatures are the same, there's no diffusion. Nothing drives the temperature. There's no way for the temperature in the middle to be 20 or 0. They'll all be 10. So, if I plug this in here, summation from j equal 1 to n of hij times c, right, is equal to the summation from j equal 1 to n of gij times 0, and this is for I equal 1 to n. So the right hand side is 0. So basically I can take the c as a common factor, cancel it out, and therefore the summation from j equal 1 to n of hij must be equal to 0 for I equal 1 through n. And there it is. I don't have to compute the diagonal elements, because I compute all the off diagonals, all the nice behaved ones, right? Remember that what we're trying to do again is calculate the singular element, which we already found out that is equal to 1/2. But that's only for linearly shaped elements. If we had general elements, what we can do is say, well, if we have elements where hij, hii might not be equal to 0, then I know for a fact that because of the equipotential condition, the sum of every row, of the hij matrix has to be equal to 0. And therefore, the element hii is equal to the negative of the sum from j equal 1 to n for j different than I of hij. So I'm basically adding up all the off diagonals. Hii is the sum of the off diagonals of its row. That's it. So we don't even need to assume that it's equal to 0 plus 1/2. We can just compute the off diagonals and then fill in the diagonals as the sum of the off diagonals, and you'll get 1/2. And that's it. Any questions? All right, so on Thursday, we'll formulate a problem, a 2D e-conduction problem. I'll provide analytical solutions to this problem. And then we'll do a BM code, an easy one on MathCAD. And we won't do numerical integration. We'll let MathCAD integrate for us to find the coefficients of the matrix, of the matrices, and then compare the solutions. And you'll see how accurate it is, even with very coarse discretizations. And then next week, we'll look into numerical integration and then doing a high-level programming language of a BM solution code, all right? So I'll see you next week. I'm sorry, Thursday.